When a system is held at constant temperature and pressure and closed to all materials, the macroscopic properties seem to indicate that chemical reactions have stopped. Our collision model, however, suggests that the reaction is not stopped, but is maintaining dynamic equilibrium. The forward rate of reaction equals the reverse rate. Under dynamic equilibrium, neither side makes a net gain. In some respects, dynamic equilibrium is a cozy accommodation between reactants and products. But what happens to an equilibrium system when it is subjected to stress? One might ask what happens to people when they're subjected to a stressful situation. One way of offsetting an unpleasant situation is to take countermeasures. Exactly the same principle is involved when stress is applied to a chemical reaction. Like any self-evident idea, though, it didn't occur to anyone until it was clearly stated by the French scientist Le Chatelier at the turn of the 19th century. If a system in equilibrium is subjected to stress, the system shifts to relieve the effects of the stress. Let's explore Le Chatelier's notion. What are the stresses that can be applied to a chemical system? Well, it can be heated, a stress we've examined in some detail. Pressure is a stress, and so is the closely related change in volume. Yet another stress is the addition or removal of one of the participants in the reaction. Now, beginning with an equilibrium condition, does Le Chatelier's principle help us to predict how stress will change a reaction? We have seen how the application of heat affects both the forward reaction and a reverse one. But will the application of heat ultimately favor the reactant side or the product side of an equation? Consider the following. 1 mole of nitrogen gas plus 3 moles of hydrogen gas form 2 moles of ammonia and liberate 92 kilojoules. It's the equation for the production of ammonia. This expression indicates that the reaction is exothermic in the forward direction. However, as we know, the equation can be written like this, which means that heat is required to decompose ammonia into nitrogen and hydrogen. So, the reaction can be looked on as endothermic from the reverse direction. In one system, we have 2 reactions, a heat producer and a heat eater. If we now add heat to the system, which reaction will be favored by this stress? Remember Le Chatelier's principle, the equilibrium will shift to relieve the stress. Apply heat. Although the entire system absorbs heat, only one of the reactions actually needs heat. The ammonia absorbs heat and decomposes into nitrogen and hydrogen. And in fact, experimentation shows that more reactants, hydrogen and nitrogen, are indeed produced until a new equilibrium is reached. So, increasing the temperature tends to favor the endothermic reaction. Now, in the same experiment, we will hold the temperature constant and see if we can predict the effects of another form of stress, pressure. Before doing so, we should look at the implications of the equation once more. 1 mole of nitrogen and 3 moles of hydrogen produce 2 moles of gaseous ammonia. Theoretically, if the reaction could go to completion without changing temperature or volume, the pressure would be reduced by 1/2. because half as many molecules would now occupy the same volume. So this reaction tends to reduce the number of molecules. While in the same way, the reverse reaction tends to increase the number of molecules. Which reaction will ultimately be favored if a pressure stress is applied? Well, a mixture of nitrogen, hydrogen, and ammonia at equilibrium occupies a certain volume. Any part of that volume has a certain number of molecules in it. If we squeeze all the molecules into this space by applying pressure, obviously the number of molecules in the space increases. Increasing molecules is the stress. Le Chatelier says we should look for the tendency that opposes this stress. The formation of ammonia reduces the number of molecules. This reaction increases to relieve the pressure stress. And once again, experimentation confirms more ammonia is formed until the reaction reaches a new equilibrium. In this case, the conclusion is a pressure increase favors the formation of fewer molecules. But does this pressure stress affect the equilibrium point of all reactions? 1 mole of hydrogen and 1 mole of iodine form 2 moles of hydrogen iodide. This means that when the reaction moves in either direction, there is never a change in the total number of molecules in the system. Increased pressure can't favor fewer molecules. We would expect no change in equilibrium, and we can test it out in the laboratory with hydrogen and iodine. The presence of a faint tinge of purple in the container indicates some iodine is present at equilibrium. If the temperature is held constant and the pressure increased by a factor of 2, no change in the color property should occur, because according to our prediction, no reaction takes place. But when we actually try it, horrors, just the converse. The purple suddenly intensifies. It appears as if Le Chatelier's principle has just crumbled. But wait a minute. Is there another explanation? In fact, what we observe is literally an illusion entirely unrelated to equilibrium. We have simply saturated the color purple by reducing the volume the color occupies by 50%. Much the way the color of a purple pattern on this screen only seems more intense when squeezed into a smaller space. Other measurements, such as massing the gas, will confirm that there was no change in the original equilibrium amounts. Being able to predict the behavior of reactions under changing conditions is vital for practical chemistry, but hardly enough. We also need to be able to predict quantities. How much will be needed? How much can be produced?